Okay folks, welcome back to Double Word Physics. This episode we're going to take a look at parallel circuits. We're going to start with the first fundamental part of a parallel circuit, which is what makes it parallel. And what makes it parallel is essentially these bits here. It's generally a good rule that if you have a junction or a choice of direction in which your current can travel, then you are a part of a parallel circuit, or at least you are a branch on a parallel circuit. The only exceptions are if this branch runs off into something like a voltmeter. Voltmeters are designed not to interfere with the circuit, so we consider that to still be a series circuit. But if you've got a choice of which kind of resistive pieces of material to go through, or which components you get to go through, then you are a parallel circuit. So take these out. We're going to start with some basic logic, that if I leave my battery, and let's say up at this point we have 4 amps of current. Then on my way down here, because there's not been a choice of which way to go, I continue to have 4 amps of current. Hopefully that makes sense, that if I come out here, 4 amps, 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 and then I arrive at this point. And if 4 amps, remember, is the number of coulombs passing a point in a sec. Basically it's the flow. Think of it as a group of people walking along. Now, if you have a choice of which way to go, then logically your group is going to split. Some of it's going to go this way, and a portion of it is going to go this way. Now, how big a portion of that depends on how difficult these two routes actually are. If the two routes are exactly the same, that they end up encountering exactly the same resistance, so let's say this is a 2 ohm resistor, and this is also a 2 ohm resistor at the bottom, then because these are absolutely identical to each other, then we are going to go with that being 2 amps that way, and we'll have 2 amps that way. We consider the wires to be resistanceless, so therefore the fact that this is a slightly longer wire makes no difference at all. As far as the current is concerned, the only thing that it's going to encounter are 2 ohm resistors. Okay, so half of it goes that way and half of it goes that way. The difference comes along when you have a system where the two aren't exactly the same. For example, if this was, say, 3 ohms and this was 1 ohm. This way is much harder to go through. The 3 ohm resistor is much more difficult to get through than the 1 ohm resistor. And electricity by its nature is a lazy animal. It vast majority takes the easiest route. You'll have heard that before. It's a little bit misleading to say that electricity takes the easiest route, but there's a preference for easy routes. Okay, so we will have more current go through the 1 ohm resistor than we will have go through the 3 ohm resistor. And in this case, we would have 3 amps go this way, and we would have 1 amp go that way. And I know this because the ratio of the amount of current that goes this way and the amount of current that goes this way is the opposite of the ratio between the two different resistors. Okay, so this is a 3:1 resistance ratio. Okay, so my resistance is 3:1, top line versus bottom line. So therefore my current is going to be 1:3. Okay, so I will have 3 times as much current in the bottom as I have on the top. Okay, happy with that, everybody, so far? I hope so. Probably a good enough time to mention that if I do something stupid like this, and I insert an extra little wire that goes down through here and up around this way, then this bottom section has no resistance. And because that is so much easier than traveling through these two resistors, then all of your current will travel this way, and this is what is called a short circuit. Okay, so this is when you short circuit something, that you basically jump with no resistance across a set of resistors. Okay, so it's short circuited. Alright, now if we actually want to do some numbers, we want to find out what the current is, or we want to find out what the voltage is, or we want to use Ohm's law in these situations, we need to begin to simplify, because this is far too complicated. So let me take out my little short circuit. I'll remove all that. Okay, and we'll get rid of these again. Okay, let's stay with 4 amps. Okay, so we've got 4 amps of current going through here. Stick with 3 and a 1 ohm resistor. Now, what we've got to answer then is how much voltage is being supplied by my battery. I have no idea what V is up here. V equals a question mark. Now, too difficult to do. So we need to simplify this into a single resistor. Okay, so we can use Ohm's law. So for parallel circuits, we get the equation that 1 over R total is equal to 1 over R1 plus 1 over R2, and so on. Okay, you can have hundreds of them in resistance. Okay, so 1 over R1 plus 1 over R2 is equal to 1 over R total. Okay, so in this case, let's do this as an example so we can spot the main mistake. We have 1 over R total is equal to 1 over 3 plus 1 over 1. So 1 over R total is equal to 4 over 3, 4/3. Pop that into your calculator if you don't believe me. Right, now that's 1 over R total. I've got it as a single fraction. So to get R total, I have to cross multiply, or I have to flip them upside down on both sides, or I multiply across by 3, divide by 1. Whatever way you want to do it, you need to get R total as opposed to 1 over R total. Me, I prefer to just flip the two fractions upside down. So if 1 over R total is 4 over 3, R total is 3 over 4. That's in ohms again. Let's go back to my symbol. Ohms. Okay, now that means that I can simplify all of this, and instead of having a 3 and a 1 ohm resistor, I now simply have a 3/4 ohm resistor. And that might seem a bit strange that it's so small, but remember, because you're giving options, then the overall resistance is going to be lower than the resistance of any single branch, okay, because you're given it a choice. It's like if you have many ways to get home from work, or you have many ways to get home from school, or wherever you're coming from. The more ways you have, the less congested those routes tend to be, because people make different choices. Okay, so V equals IR again, and that's the way we want to keep it. I want to get off symbol and back to marvelous Comic Sans. V equals IR. So V is equal to 4, which is my current, multiplied by 3 over 4, which is my resistance. So my voltage is equal to 3 volts. No need for the calculator on that one. Simple as that. Once again, break it right down, and that brings me back to a single resistor with a single current and a single voltage coming in. Now, one of the key things about parallel circuits is using the fact that voltage, if we say this is 3 volts, voltage is the amount of energy given to each coulomb of charge. Isn't that right? Okay, so if I've got a little coulomb of charge coming out of here, he's carrying 3 volts, and he comes along here, and he goes along, and he drops off his 3 volts and heads back with no voltage. We discovered that in our first kind of lesson. So let's run our way back to what we had at the very start. We had a 3 ohm resistor and we had a 1 ohm resistor. And we've discovered that our overall voltage is 3 volts. So let's see what other things we can discover from here, just using Ohm's law. Okay, because remember, Ohm's law can be used across the whole circuit or between any 2 points. Right, so logic time. If I'm carrying 3 volts and I come along here, I go still carrying 3 volts, haven't been abducted or beaten up by anything. And I come along here, then I go still carrying 3 volts, get the absolute bejesus beaten out of me by this 3 ohm resistor, lose all 3 volts, and head back round. Okay, so that means that because the other coulombs that are going through there are still carrying 3 volts, that this is a 3 volt using resistor. Could have made a different choice though. I could have gone along here. I was doing fine. Still got 3 volts. Still got 3 volts. Still got 3 volts. Alright, I get the crap kicked out of me again. And I go through here and back up and around. And remember, I have to arrive back with 0. So I have also used 3 volts in that bottom one. And then one of our key parallel circuit rules is that the voltage across each branch we'll talk about what branches are, is the same. And we don't say the voltage across each resistor because if I was to get super complicated, I could put another resistor in here and he'd arrive with 3 volts, but he'd have to share the 3 volts between this one and this one. Okay, the overall voltage being used by this whole branch is 3 volts, but it might be separated between multiple resistors. Okay, so a branch is from the point at which you get a choice to the point that you join back up again. That's what a branch is. And so if you're taking notes, that's quite a good one to take. You know, what is a branch? It's where you get a choice and then you join back up again. That whole bit is a branch. Is the voltage across each branch is the same, but the current is shared between the branches. Now I hear you asking how much current could be going along that, and we've already worked that out. We worked that out by logic and ratios and resistances, but we can also do it by calculation. If I take Ohm's law between here and here, I know that this is a 3 volt user and this is a 3 ohm resistor, so as a result I can use I equals, take off the underline there I think, I equals V over R, so I equals 3 over 3, I equals 1 amp. Okay, just like we got before, this is 1 amp on here. Logically we know that the other one's got to be 3 amps because it needs to make up 4, but we can prove that. If we take Ohm's law between this point and this point, okay, then we go back and we use, remember to turn off my underline this time, if we use I equals V over R here, then we get I equals 3 volt, again divided by the resistance which is 1, so I is equal to 3 amps, just as we had before. So you can do it by logic, you can do it by ratios, but more importantly you can do it by Ohm's law if you apply a little bit of the rules of parallel circuits. And that's all there is to it. Parallel circuits, dead easy. Next time we'll have a little bit of a chat about why lengths and resistances can be changed when you change materials.